Joining us from Norway and from NILU, one of the elite research institutes in Norway, we have my colleague, Sabine Eckhart, and she'll be talking to us more about atmospheric impacts of wildfire in the Norwegian Arctic. Over to you.
So actually, when Jessica asked me to give a talk about wildfires, I realized that even when I started my work here at NILU in 2006, this was actually the first topic I was working on. And since all these years, it permanently followed me. I mean, later on, I was working in the AMAP group for short-lived climate forcer, and there the black carbon, which is also released by biomass burning in forest fires, is very important. And also, as we have observations at the Zeppelin station, which you see in my background, there are many scientists which try to understand if there are enhancements in pollution, and very often these enhancements are fires. And I was so happy that I could collaborate in many of these studies, and I learned a lot. And so hereby I want to acknowledge my colleagues I could work on fire together with. So this is a map of Svalbard, where we have our research station. It's in the high Arctic at 78 degrees north. And it's established in 1989, and it has a focus on long-term measurements, which are very important to see if there are trends in certain substances. It's part of many global and European monitoring programs, and recently there was a paper describing all these observations and the long-term trends by Platt et al., which gives a very nice summary of 30 years of observations. So what you see here is the nice view from this station here on the left-hand side. And in 2006, the view was, the visibility was drastically reduced, and it became very hazy. And when looking at the observations during this time, which I show here a curve, this is, for example, CO, which we know is an emission from biomass burning. We saw in 2006 that there were record high enhancement in CO, in black carbon, organic carbon, and also particulate matter. So I'm working with transport modeling. So what we did is we performed backward calculations from the Zeppelin station to find out where the air masses come from. So this is quite similar to trajectory methods, which we've seen before, but it's more quantitative. So you can actually calculate how much fire emission or other emission contribute to the measurements at the station. And what happened in 2006 was really that the transport model showed that the emission which were recorded at the station could be led back to areas in Russia, where there was at one hand agricultural burning, but also this agricultural burning induced other wildfires. So it was very intense emissions, which were directly in very short time transported to Svalbard. So this was a second event. So a similar event, not as strong, happened in 2004, and this was then in 2006. So many scientists argue that this is kind of the start of a change in regime. So we know with climate warming, we expect more fires. So it was kind of expected that these events will become more intense and will also happen more often. So one motivation of the analysis I will present now is how did it develop since 2006? Was it really that there are more frequent fire emission at Zeppelin? To give a quick, short introduction, what I will talk now is I will talk a bit about which chemical species are emitted from this fire. Look at observations, how you see the fire episode in the observations. what statistical method can we use for identification if we had fire plumes. Then I will show some case studies for the Zeppelin station, and then I will talk briefly about total column observation. So now we go back to 2006, and here we see what I've shown before, that, for example, equivalent black carbon went up to 880 nanograms per cubic meter, which is very high value, and it's well aligned with the other pollutants measured. So there is a small peak in end of April, and then a larger peak beginning of May. But then we looked at the station, we record many other pollutants. We could check all other pollutants, and we saw that also, for example, ozone was high. We could see high mercury. The persistent organic pollutants were really high, which we think was because of a re-emission after the fire. But also the weekly samples of levoglucosan or sulfate, nitrate, and potassium showed a clear elevation during this episode. So now it's the question about the trend. So we saw that black carbon is a very good indicator for fires. So in the newest AMAP report, we investigate long-term black carbon observations. Here you see it from 3 Arctic stations. The lowest level shows Zeppelin, looking for trends in black carbon. So black carbon doesn't only come from fire, it comes from incomplete combustion, and it also has anthropogenic sources. Due to many convention and reduction efforts, the concentration or the emissions in black carbon are decreasing, and this negative trend can also be seen in the Arctic stations. So we see here the blue line that there is a negative trend at all the stations. However, if you only look at the summer trend, you see that it's much lower or even positive at Zeppelin. And the question is if this can be led to wildfire, which only occur in the summer season. So now I made an analysis. So I took black carbon because we found it's a suitable tracer for biomass burning. It's also suitable because it has a very short lifetime. So you see quite distinct peaks if there is a fire event or any other pollution event. So I made here an analysis where I calculated the monthly median for every month. So here it's from January to December, and then 1 bar for each year. And what we see quite clearly in this is that during the winter months, also the trend is decreasing, while during the summer months, it's more stable. So as I said, black carbon has a very short lifetime. So very often the background is very low, and then I have distinct peaks. And these peaks I can see best when I don't look at the mean values, but here, for example, I look at 20% of the highest values in the data set, and then we can see distinct fire events. But the question is now, how do we know that we have a biomass burning event at the station? So the problem here is that black carbon can have different sources. So it can come from combustion of wood, for example, or fossil fuel. And fossil fuel, the distinction here we can make by forming isotopic analysis, or what I will explain later, we can perform a positive matrix factorization analysis to see if it comes from biomass burning or fossil fuel. What we cannot do is, as biomass burning is also from domestic burning and from wildfires, we both burn wood. So it's very difficult to distinguish here where it comes from. So for this, it's useful to have model simulations, which can show the source region and sources. So I was explaining before about these statistical methods. So this is a study by Carl et al. From 2019, and it makes use that in Zeppelin many different aerosol components are measured. So what they did in this study is they took many aerosol components, and then they established with a PMF, I don't have time now to go into this, a factor profile and a factor contribution. The factor profile shows which chemical components are important for the aerosol type, while the factor contribution shows how high each aerosol type at each time step was. We at NILU, we do a similar thing, but we don't use different chemical components, but we use different wavelengths from an atolometer, and then we can also come up with absorption profiles and concentrations and distinguish the observed black carbon if it comes from biomass burning or from fossil fuel. So now I'm going back to what I've shown before, and with case studies, I will go into the highest episode and see how we can see if it was biomass burning. So here is the episode in May 2006, which is much higher than the scale here. So it went up to 800. And then there was another very strong episode in July 2015. So here this was the year where this PMF analysis was performed, and we really see that it identified in July 2015 this episode as the biomass burning aerosol. We see here a trajectory analysis which goes back to Alaska, and then we see here this is all of July. This is black carbon and CO, and also the PMF analysis. And it shows that most of the black carbon aerosol arriving in Alaska was really from biomass burning. So the next episode I want to explain wasn't really especially high in black carbon. It was in July 2020. Here is the colored plot is a FlexPath calculation, which shows the source region of the air masses which reached Zeppelin, and the gray circles are fire emissions which were transported to Zeppelin. So the gray circles are only plotted if the emissions from them were transported to Zeppelin. So we see it's a lot of Russian emissions which were in very short time transported to Zeppelin. Here, if we look at the monthly plot, we see a distinct peak in black carbon. We have 2 episodes, and for the later episode, it's very clear that it's biomass burning. With FlexPath, we can also put in other emission inventories, so we can also see that, for example, it wasn't only biomass burning, but also industry, shipping, and domestic burning contributed to this enhancement. So what's remarkable for this episode is it wasn't really the highest one in black carbon, but if you look at other substances, these are here from a weekly sample, it had the highest organic carbon and the highest levoglucosan from the last 4 years. So it was quite a remarkable episode. So the last episode was in August 2019. It was also quite high. But if you look into it, the model results show it wasn't biomass burning, but it was mainly an episode of anthropogenic pollutant. Then I made a statistic from which region, if there is biomass burning, from which region it comes for the last 4 years. So I used daily emission data and FlexPath runs. And we can see that it's highly variable. So sometimes, for example, 2017, North America, Canada is a very important source, while in other year, Eurasia is the main source. Then if we look statistically how the biomass burning aerosol is located over Zeppelin, so I want to draw the attention to the right lower plot. So this is the height against black carbon concentration, and we see that the biomass burning aerosol, not the biggest fraction arrives near the surface where we can record it by the station, but most of the emission arrive in 2 kilometers. So this shows that it is important if we want to capture the whole biomass burning aerosol, that we can't only look at the surface, but that we also have to look at the total volume. So therefore, we also looked at CO as derived from satellite. So you have 3 time series. One is the black carbon at the station, one is the CO at the Zeppelin station, and one is the satellite. And the blue circle shows the time where a really intense plume went over Zeppelin, which was only partly recorded at the station. So if we want to make statistic how much biomass burning aerosol is transported into the Arctic, it's also important that we look at the total volume and not only at the surface. So here in the last plot, I show analysis from the sun photometer. And in the upper plot, this is the year 2019, while the black dots are like the annual average between 2002 and 2021. And we see, for example, in 2019 that there was much more than average aerosol in the atmosphere. However, with this analysis, we can't really identify if it was volcanic aerosol, dust, or biomass burning. So we need a combination of more methods. And to conclude, so the wildfire episodes are clearly visible at the Arctic station Zeppelin, sometimes even seen with the bare eye. The wildfire emission in 2006 were still the highest on the record. We see a negative annual trend in black carbon, but a positive trend in summer, which gives an indication that there is some summer activity, which are likely wildfires. Looking at the episode, very often we see that it's not purely biomass burning transported to the Arctic, but if there is transport to the Arctic, it's often a combination. So it's anthropogenic sources together with wildfire sources, and we need statistical method and transport model to disentangle these 2 sources. This can also be done by using statistical methods, and modeling studies show that North American and Eurasian continent is a source to wildfires, and this is highly variable over the years. The climatological average of the model simulation showed that the biomass burning aerosol is transported to higher altitude, and therefore it is important to have a combination of surface observation and total column observation to investigate the biomass burning aerosol. Okay, thank you.
Thank you. That is wonderful and fascinating. We have a question from early on in your presentation. Could you return to the slide that shows the mercury emissions? One of the questions is very interesting mercury data. It appeared that there were both enhancements and depletions of gaseous elemental mercury of GEM. Do you have any thoughts about this? The specific question is there rapid oxidation caused by an uptick in some atmospheric oxidant from fires, or halogen releases from the oceans, or some mixing of these 2?
Yeah. I mean, the mercury chemistry is very complicated.
Yes.
I think I can't really give an answer to this, but I can investigate with my colleagues and follow it up later in the Google document.
That sounds fantastic. Yeah, I think that's why we have the Google Doc. That's a good question. And then one question was that you showed us the source model has some predictions of significant biomass burning contributions from South America.
South America.
Yeah, so is that somewhat unlikely to have extensive interhemispheric mixing? So, I think it is. No, I think it's just where you had that one where you showed a little bit of the globe. But it's just that you're running global models, right?
Yeah, I run global model, yeah.
And so, but sometimes there are global estimates, but you're really looking at the regional impacts from those global models to the Arctic. Is that?
Yeah, I mean, I would have fire emissions from all over the globe, but I mean, as we know, black carbon has on average a lifetime of 7 days. So the source region of black carbon, which is transported to the Arctic, is very limited.
Right. So it's unlikely to ever have this kind of interhemispheric mixing. Yeah. Well, there are more questions for you in the Google Doc. And I want to thank you so much for joining. This is a great bookend to the work we saw from FMI earlier. So thank you so much, Sabine.